Okay, so welcome back, and so here's the next part here. So we're going to do the base step, or the base case, and we're going to start with the first row, I equals 1, okay, and so we're going to let L sub I be the column number of the leading entry in row I, okay. So we're going to consider the entry of each row that is in column L sub 1. Okay, so since we're talking about I equals 1, we're going to start with the first column. Now, keep in mind that if there is no non-zero row in the first row, so in other words, we're dealing with the zero vector, then this would be vacuously true. Okay? Right, so if there's no such non-zero row, so that R ends up being the zero matrix, then the lemma holds vacuously. Okay, so we're just gonna, so that's automatic. So we're not gonna consider that. But so let's say we have this situation where we're in L sub 1, right? So the leading term, or excuse me, the leading coefficient, or the leading variable. Column 1. And so then the equation gives us this, right? So we can write 0 equals this linear combination, okay? Where we have a linear combination of all of the rows, right? So we have these scalars, right? And so now keep in mind that the matrix is in echelon form, right? So the matrix is in echelon form, so every row after the first has a zero entry in that column, right? Because it's in echelon form. So since we're dealing with the first column, so every entry below it is going to be 0, which tells us that R sub 2, comma L sub 1, all the way through R sub m, comma L sub 1 is equal to 0. Now, what does that tell us? Well, if all of those are equal to 0, then that also tells us that C sub 1 is equal to 0. Why? Because we know R sub 1 comma L sub 1 is not equal to 0 because it's leading. It's the leading entry, right? So, and it has to equal 0. This whole thing is equal to 0, so that the only conclusion is C sub I is equal to 0. And that takes care of our base step. Okay? Now, in the next video, we're going to talk about the inductive step and wrap up the proof.